Hello, this is Picture Me Coding with Eric Aker and Mike Mull. Hi, Mike. Welcome to your show. It's a weekly thing.
It's my show now?
It's your show. It's your show plus my show. Randy said I'm the host. You're the guest. Welcome to my favorite guest.
I thought I was co-host 9000.
Co-host 9. Did you know there's a new Wilco album out?
You know, I did not. I don't know. Seems like maybe there's a new Wilco album every year, but
Yeah, okay, so in between Sky Blue Sky and this year, I didn't hear a lot of stuff that made me think I want to listen to this again. But they have a new album out called Hot Sun Cool Shroud, and I think it's pretty good. It reminds me of the Wilco I liked, Sky Blue Sky, Yankee Hotel Foxtrot. There's a song on there called Ice Cream that's pretty good. There's a song called Annihilation that's pretty good. And it sounds just like a song from Wilco that you would like. So I recommend you check it out, my friend.
Sounds cheery.
Yeah, it's not bad. Annihilation, Ice Cream. Two sides of the same coin there in Chicago for them.
I will check it out. Somehow missed that one.
Yeah, it's not bad. What about you?
So a few days ago, I watched the Yacht Rock documentary on Max.
What is Yacht Rock?
So the documentary lays that out pretty nicely. But one of the things they point out is that the sort of progenitor band of all this Yacht Rock was Steely Dan.
Oh.
Michael McDonald, also, who's kind of like the godfather of Yacht Rock, did the some of the background vocals on Steely Dan's Asia. So anyway, the reason I bring this up is because the album I've been listening to a lot is new Father John Misty album called Mahashmashana.
Oh.
And I'm sure knowledgeable people in the musical industry would disagree with me, but I sort of feel like he's the spiritual heir to the Steely Dan throne. You know?
I heard an interview with him once, and I was like, wow, this guy seems kind of insufferable. I don't think I'm ever going to listen to his music.
Yeah, some people just absolutely hate him.
So that's a common response. Yeah, why is that, you think? Do you know why?
I don't know. I think he is pretentious to a certain extent.
Yeah, that's what it was. He just seems so arrogant and like disgustingly self-involved.
Yeah, and his music has got this. It's very distinctive. There's a little bit of jazz vibes, and they're very slickly produced. And his lyrics are cryptic and sometimes a little self-indulgent. But anyway, I guess I have to say that I like this album quite a bit.
You like this one. But here's my question for you. Do you like Yacht Rock?
So I have this mixed emotions about Yacht Rock. So the sort of heyday of Yacht Rock happened to be when I was in high school. Mm. So I've heard so much of it. These Michael McDonald songs and Kenny Loggins songs I have heard so many times, whether I liked it or not, that no matter how good the songwriting is or the production is, I never want to hear Toto again. If I'm like if I'm in a mall or something and I hear Toto, it's just like I leave that store.
That's like my friend Saw. If he's at a party and the Red Hot Chili Peppers comes on, he's like, I'm leaving.
Yeah. I know a lot of people with that reaction too. Anyway, it's a good album. If you can handle his demeanor, it's interesting musically. Not a lot of like snark on this one. So I like a lot of the songs on here. I do have to warn you though that there's 8 songs and it's a 50-minute album. So if you do the math, that's more than 6 minutes per song. So, but yeah, it's a good listen. It's ending up on a lot of end of year top albums lists. So I don't think I'm totally crazy in thinking that it's a good album.
Okay. All right. Mike, last week we talked about a few of our favorite algorithms. You did fast Fourier transforms. I did hyperlog. And after reflecting on it, I felt a little bit proud of my hyperlog description. That's a hard thing to describe, and I'm giving myself a little pat on the back here. I think I did okay. We try to do this without any kind of visual representation. Obviously, we're just using our voices, sending them out into space, and hoping our voices can populate some fantastical ideas in the minds of the people who hear us. That's hard. That's a hard thing to do. I want to try to do it again. You want to climb that mountain again?
I'm going to give it a shot. I always feel like I kind of went to a museum and saw a famous painting, and I'm coming back and saying, "Let me describe this painting to you." But
and you have a habit of picking extremely mathematical paintings to follow your metaphor.
Yes,
So
I'm not sure what the mathematical equivalent would be in a painting, but
you're going to tell me about. I'm going to tell you about some. You're going to tell me about some. I think we're going to pick some shorter ones, hopefully, this week. Hopefully, they'll be a little shorter. Last week, we just had enough time for you to do one, me to do one. This week, we're going to do a couple shorter ones and really going to try to hit the high notes here. So, listeners, you got to tell us, did we pull this off or did we crash and burn on this one? And a little note for Mike before he starts. If you start describing mathematical formulas where you're saying, and then I have a square root of I plus v squared all over, then you're probably going to lose at least one listener, and that's me.
well, my next algorithm is a pretty simple one, but I will have to digress briefly to give you a quick lesson in abstract algebra.
Oh, geez. Okay, I'm ready for it. And then remember, if you're listening to us, you can reach us at podcast@picturemecoding.com. And you can tell us whether we pulled this off or not. This is our ambitious trying to describe algorithms on the show. Okay, Mike, take it away.
And you can look us up on Blue Sky too, which is the cool new kid on the social network blog.
Oh, that's true. Yeah, you can see us on Blue Sky. You can talk to us on Blue Sky if you want to.
So my algorithm is the Diffie Hellman key exchange algorithm. And again, this is another one that sort of stretches the notion of algorithm because there's, in addition to being a series of steps, there's also sort of like a cooperation between individuals that's required here. But first of all, let's talk about what a encryption key is. So if I want to send you messages that are encrypted and so that you can decrypt them, then the two of us need to share a key. In this case, the key is a number. It's a sequence of bits, basically.
Mm-hmm. Like 4? Is that a good enough number? Did I pick a good one?
That'll work fine. Yeah,
it'll work. Okay.
Yeah, as long as it's 1,000 bits, but you only set the second one or the third one. Then
I got a lot of zeros in there. Okay, all right.
So I need the key. You need the key. If that were the end of it, then I could probably just put it in a suitcase with a padlock on it and have somebody deliver it to your house, and that would be the end of it. But
well, wait. Let's go in the real world. This happens all the time when I go to a website and it's over HTTPS, right? Like I need to encrypt my traffic so that as it bounces around the internet, every server along the way doesn't actually read what I'm sending. If I send to you my username and password through a web form, it's going to bounce around all over the internet. It's going to land at my bank's server someday. I don't want everybody along the way to see that. I want to encrypt that traffic. We have to first agree on how we're going to do that.
Exactly. And, in the modern world, this is commonplace, but in the early 1970s, when people were building these tools, the idea that we were going to be having, frequent encrypted communications with an indefinite number of other parties with whom we may or may not, have a history was kind of a leap.
Yeah, actually, let me jump in real quick there. Sorry to interrupt. So, it's possible that if I were going to go to one banking website forever, I could just have some sort of key that I have with them forever. But if I'm going to need a key with every single website I might visit on the internet, then that's pretty mind-boggling, right? I need some way to come up with a strategy to encrypt communication on the fly. That's what we're talking about.
That's part of it. And then also you need to be able to do it in such a way that you're not revealing anything to the other party that would allow them to potentially decrypt data that you send to somebody else.
Mm-hmm. So I'm going to tell you a secret, but it's completely unrelated to any secret I've ever sent to anybody else.
Right. And, if you are working in the industry, you're probably already familiar with RSA and, public key encryption and so forth. And you probably have a private key or many private keys sitting on a local computer. But these were novel ideas in the mid 70s. So in 76, two guys, Whitfield Diffie and Martin Hellman, published this paper called New Directions in Cryptography. And they talked about several aspects of cryptography, but one of the things that they introduced in that paper was this key exchange protocol. So the idea being that you want to send a key, in this case for symmetric encryption, you want to send a key to some third party, but you want to do it in such a way that it's secure, and you want to do it in such a way that the key that you send them is not, it's not the same key you send to every party. You want it to be unique to
Mm-hmm.
that particular individual.
Mm-hmm. Mm-hmm.
So this is where the lesson in abstract algebra starts.
Can I ask, do you know, so we're talking public private key cryptography? Is this public private, or it's not public private yet?
So that's a good question. This is regarded to be a form of public key cryptography. It is a symmetric key. So the difference between, in fact, this has sort of been established in legal precedent as one of the first instances of public key cryptography. Anyway, so it depends on something called a finite field. And
Wait. Sorry, you were just about to define asymmetric versus symmetric. People may not know the terms.
right, okay. So just sort of briefly, the idea is that with symmetric encryption and decryption are done with the same key. So,
Yeah.
The
We both
objective
have
here,
the exact same password we're using to decrypt and encrypt things. It's symmetric.
right? So if this algorithm does its thing, then you and I will both end up with the same key, and we can use that to both encrypt and decrypt. And
Mm-hmm.
RSA, by contrast, is asymmetric. So I have one key and you have another key, which is my public key. And so if you want to, you can encrypt something with my public key, but you can't decrypt it.
Yeah.
So I can only decrypt it with my private key, and vice
So,
versa.
and asymmetric is and public private key cryptography wildly popular. It's used probably millions of times every day around the world.
Yeah.
JWTs, OAuth, all kinds of SSH, huge numbers of things rely on asymmetric public private key cryptography. But this is a precursor to that.
Yeah. If you're using the internet, you are using, some variation of this. The Diffie Hellman paper, the Diffie Hellman algorithm is described in their 76 paper, uses what's called a finite field. And really, the key thing with a finite field is that it's this set of things on which are defined the operations addition, subtraction, multiplication, and division. Or sometimes people call the division operation the multiplicative inverse. But in any case, it's just this sort of abstract idea that originated with Galois, if you know that name, Évariste Galois. So sometimes people also call it a Galois field.
Oh, but it's like a field like in math or category theory where it's like, I have a group is things I can add and subtract, or
yeah, it's a group as well. So where was I going with this? Okay, so
you're talking about field. Go ahead, sorry.
Right, so you need to have this finite field. In the case of the Diffie-Hellman algorithm, the finite field is a set of integers, the size of which is a prime number.
What does that mean? The
So
size of which? The size of the set?
the size of the set is typically a prime number.
Okay.
It doesn't have to be in a finite field, but I don't want to go into that too deeply.
Okay. So I've got a whole bunch of prime numbers in a set. Oh, sorry. I've got a whole bunch of numbers in a set.
Yeah.
And the quantity of them, the cardinality of that set is itself a prime number.
Right. And since it's a finite set, then you probably will figure out pretty quickly that the the math is mod that prime number.
Hmm.
So if, say, the set were, had 7 elements in it, then if you did 3 times 4, the result you want is actually 3 times 4 mod 7 or
Hmm.
5. So, you want the result of the multiplication to also be in the field.
Okay.
If you do 3 times 4, that's 12, which is not in the field. But if you do 3 times 4 mod 7, that's 5, which is in the field.
Okay. So it's almost like I have a clock face, and I'm just spinning around the clock to pick one of these numbers in the field.
Yeah, that's a pretty standard way to describe the modulus operation if you're not already familiar with that. In practice, that prime number is a very large number. I think in modern systems, it's probably going to be like 2048 bits or something like that.
So this is a clock face with 2048 bits of numbers.
Lots of potential numbers.
2048 to the power of 2. 2 to the 4, 2 to the 248 is what.
Yeah, so potentially a very big number. So the first thing that happens in this algorithm is that each party that wants to exchange information generates this number. It's a number that's in the field, and it can be more or less random.
Okay.
There's some criteria on what makes a good number here. So in practice, it's not totally random, but just think of it as a uniformly selected random number from the
From
field.
the field, from the circle of numbers. What is our goal to converge on the same one ultimately?
What do you mean by that?
We're both going to eventually try to, this is symmetric in cryptography. We're both going to try to do something where we end up with the same number in the field.
Right. That we definitely want to end up with the same number at the end, but at this point, each party is just choosing this sort of secret number
Okay. At random, kind of.
at random. So let's say each party has this random number, which we will call x, and then you can calculate, because you can do multiplication in a finite field. You can also do exponentiation, and so one of the key elements of pun intended, one of the elements of Diffie-Hellman, which is important, is that you end up calculating a number which is where you use x, this randomly selected number x, as the exponent
Hmm.
to calculate a new number. So you
And the new
calculate.
number is also in the field.
It's also in the field, yeah. So you calculate this new number y from x by taking this number called alpha, which I won't go into too deeply, but it's going to be the same number for every party. You calculate alpha to the power of x mod q, where q is the size of the field.
Mm-hmm.
Now, the interesting thing about this, and the sort of important insight of Diffie-Hellman, is that it's easy to calculate y given x, but it's very difficult to calculate x given y.
Oh, okay.
The hope then is that since x would be difficult to determine from y, it's fairly safe to share y with another party.
Hmm.
So this y value essentially becomes the public element that you can share with another party.
But if I'm the client and you're the server, we both ended up with different Ys because we started off with different X's.
That's right. Yeah. So at this point in time, you can think of each party who you might want to communicate. You and each party that you might want to communicate with should have a unique version of Y.
Mm-hmm.
So if somebody wanted to calculate your secret X value, they would have to solve what's called the discrete logarithm problem, which is even to this day assumed to be computationally intractable.
So they can't guess my X. They just see the Y. I could share the Y. You can't guess my X.
Yeah, unless you have a quantum computer, in which case, all bets are off.
All bets are okay. Well, I'm not going to worry about those.
So the second sort of key aspect to this algorithm, important aspect to this algorithm, is that we want to calculate a shared key.
Yeah.
So the shared key, mathematically speaking, is going to be taking this number alpha and creating an exponent, which is my secret x and your secret x mod q.
Hmm. But if I
So
can't calculate your, sorry, you're going to
no,
answer. I'm on the edge of my seat here. I want to get to a shared thing. I want to know
yeah.
how everybody at the restaurant ended up with the exact same sandwich by ordering something different.
Yeah, so go ahead and ask your question because I think it's important.
Well, I don't understand how I get your x in order to get your x times my. Let's say mine is called n and yours is called x. And how do I get the exponent of n times x? I don't know what yours is.
Right. So that's the magic of Diffie Hellman is that you don't know my x, I don't know your x, but we each know each other's y. And so if you look at the algebra here, what we're trying to get to is alpha to the power. Let's say that mine is xi and yours is xj. What we're trying to get to as a shared key is alpha to the xi xj mod q. I know xi, but I don't know xj. You know xj, but you don't know xi. But if you look at the algebra here, if I take my y value, if I take your y value and take it to the power of my x value, then that turns out to be alpha to the xj and alpha to the
Oh.
xj is the
Oh.
exponent's commutative, so alpha to the
Okay.
is the same as alpha to the xj.
Okay.
So just by knowing your y and you knowing my y, we can each calculate the same symmetric key.
Okay. It's like if your ladder is a black box, but I stack it on top of my ladder, I can end up at the same place you ended up at.
Yeah, so we both end up with the same symmetric key in the end, but because of the way the math works, we never have to reveal our secret number to
Hmm.
each other. And we also end up calculating a key that is unique to our particular exchange. So
Because we started with a random number. But
right.
if you had an observer just listening to all these communications, I mean, it's not going to, that's still, they're not going to be able to, they're going to be able to figure out the same thing.
Yeah, there is a little bit of a man in the middle susceptibility to Diffie-Hellman. If someone can intercept both your public key and your encrypted transmission, then it's conceivable that they could decrypt a message that was intended for somebody else. So,
Hmm.
there typically has in this to make this totally secure, there has to be some added stuff to make it a little bit more safe to get around man in the middle attacks. But
That's probably true of any symmetric cryptography, I would bet, right? I don't know. Maybe that's out of my pay grade
yeah,
answering that question.
that makes sense to me too. In any case, I know that describing math in words is a tricky thing, but I think you can. I hope you can see that this series of steps allows us to arrive at the same symmetric key.
Yeah,
And
I gleaned it in the end. I've never understood Diffie-Hellman. That's pretty cool. Thanks for describing that to me.
this is still a pretty commonly used algorithm. It's been modified in various ways since Diffie and Hellman described it in 1976. And a lot of times people use a modification that instead of using a finite field, uh, the way they used it, it uses elliptic curves.
Mm.
Um, but there's an option in the TLS protocol where you can use Diffie-Hellman to exchange keys. I believe it's called the Diffie-Hellman ephemeral protocol because instead of having like a preset private key for each user, the algorithm in TLS generates a private key on the fly so they can do this key exchange.
Okay.
Um,
Would you do that as like more of like a retro computing thing? Like, oh, let's go back to Diffie-Hellman in the 70s. That's a little more of a cool retro, kind of like riding a surfboard without a leash.
no, I think there are still cases where this is used. Like I said, it is an option in TLS, and I think people use it in other ways too. One of the nice things about Diffie-Hellman is the key you end up with is a symmetric key, and that symmetric encryption is generally quite a bit faster than
Hmm.
asymmetric encryption. In fact,
That's pretty cool.
I think with asymmetric encryption, you typically just use it sort of like at the beginning to exchange a symmetric key anyway.
Well, I'll tell you one that I always kind of liked.
Go for it.
I always liked heaps and trees. Not graphs so much, but trees. I don't know. Something about trees just seemed pretty cool when I learned about them. And I actually had this project I started maybe 10 years ago where I was like, I want to learn about all the different trees I could possibly find. And I called it 52 trees. And the idea was I'll study one tree every week. But unfortunately, I've forgotten most of those. I know that, and this is like, I feel like this example, if you say, well, what's a favorite algorithm of yours? I feel like, oh, these are so basic, like they're uninteresting, they're dull, but they really felt magical when I first learned about them. The first one that really struck me as pretty cool was a binary heap, which I feel like even the words come out of my mouth. I feel like that is so basic. But the reason I found it magical was it's like I've got an array and I can intuitively find, like if it's a min heap or a max heap, I can easily find the min or the max in this data structure. Extending off of there, the next one that I found intuitive that made a lot of sense, but also had practical application for me was the radix tree. It's also called a prefix tree or a compact prefix tree or a Patricia tree. It has a bunch of names. It comes from an original paper in 1968. The Patricia tree is actually, it's an acronym. Practical algorithm to retrieve information coded in alphanumeric. And in the paper, they give examples of you go to a library, you want to find some information using an index. The index has to have enough relevant stuff so that you can then look up things in the library. But the prefix tree, the radix tree is a pretty cool data structure. And there it is already. I'm not sure if you're going to ding me for it because it's not quite an algorithm, right? It's a data structure. The idea is that you could take strings and you can look at the shared prefixes for those strings, and you can build a tree based on prefixes. So, for example, I could take a set of strings, a set of words, maybe like testing and treats and trips and teeth and teething and toast. And I can actually build a tree out of all of the shared prefixes of all of these words. And the leaves, the endpoints of that tree, are the remaining suffixes. So all of these start with the letter T. So my first node is T. And then some of them have R, and some of them have E, some of them have I and S and stuff. So you end up with this like tree that is based on the prefixes, but it's not single character, it's the entirety of the shared prefix. So if I had treats and trips as part of my tree only, they would share the TR, and then I'd have a child off of the TR node that's the eats, and a child off of the TR node that's ips. And the interesting thing is you can pretty efficiently find stuff. The efficiency comes from the fact that you're really only going to traverse the height of the tree, and you really just need to do like a character by character search for whatever input string you're looking for. Now, I've never tried to describe this completely with audio, without a whiteboard. I have no clue how I'm doing here. Is this making sense to you? You probably already understand the data structure, so maybe that's not you're not a great audience for me.
Uh, yeah, I guess it helps a little bit to already have some familiarity with it. But yeah, I think you're doing fine. It's interesting because when I hear the word radix, I immediately think of radishes. And I believe radix means a root, the original Latin word. I'm not sure about that, but which sort of makes sense if you listen to what the thing is doing. You know, you're sort of starting with the root of each term and building out from there.
Yeah, you try to split using as many shared characters as possible, and you end up with this tree of shared prefixes for all the input strings. Now, you could use this for like autocomplete, but the interesting thing is this type of data structure is actually used frequently in web frameworks in their routers. So if I have a web framework and I want to give you, the developer, the opportunity to write like an HTTP handler, so request comes in, those requests are associated with particular paths, and you're going to write a handler. If you think about maybe a typical CRUD API, there's a lot of like duplicated prefixes in there, right? I'm going to have a resource, maybe it's a shoe store. So I've got shoes and I've got shoe sizes, and you may have shoes/size and then a size integer or something like that. So if you look at like in Golang or Node.js, the routers in Go, it's called Fast Router. I can't remember the name of the one in Node.js. If you look at Axum, the Rust web framework, they all use radix trees to look up routes. People also use radix trees to look up IP addresses. It's a sufficient way to store shared prefix trees. And years ago, I did some work for the Starlet web framework. It's a Python async web framework, which is actually what Fast API is based on. So I wrote cookie handling for Starlet, did a few other things, and that work then ended up getting is now used in Fast API. So I've actually written some stuff that's used in a lot of people's code. Is that Fast API is pretty popular, surprisingly, not surprisingly, but I was surprised when I started looking at Starlet. They use a list of routes, and they do just a linear pass over that list of routes whenever doing route matching. This is fine if you have a small number of routes, but generally when you get over like 100 routes, more efficient data structure is advisable. And so I was like, wow, they should really use radix trees like these other frameworks. So I wrote a Python HTTP router using radix trees. I called it Tokamak. Sidebar, that's my favorite name for any open source project I've ever worked on. But anyway, so Fast API and Starlet still use linear pass over a list of routes to look up to match a route, to match an endpoint. And I wrote this radix tree router thinking, you know what, I'll try to eventually make it applicable to Starlet and lobby them to put this in. But I never had the will for the second part. And around the same time that I wrote Tokamak, the author of the latest router that's in Verkzoid, which is what Flask is based on. So this is a core contributor to Flask. He was working on a router for Flask and making it more efficient. And he was using a kind of modified radix tree. So we were bouncing ideas back and forth. I ended up building a benchmark based on his router, and my router and his router are about equivalent. Mine tends to handle mostly static routes better than his. His tends to handle a lot of dynamicism where it's like you can inject different parameters. So radix trees, I find it kind of cool and magical that you could build a tree to efficiently look up strings like this, and that they get used in HTTP routing and IP address lookups and things like that. It's used all over the place. I think that's pretty cool.
Very cool. Here's an important computer science question for you.
Uh-oh.
TRIE, is it pronounced tree or is it pronounced try?
I know it comes from retrieval tree. I would love to pronounce it tree. The problem is, and that goes with the German too. You know, the German is IE's the second letters sound. My German teacher used to say, "Ich trinke Wein in Wien." Anyway, it's pronounced try, and I find that disappointing.
I've heard people pronounce it both ways, but it's very confusing when people pronounce it tree. So
Yeah, I think their ship has sailed on that one. I don't think you can call tries trees.
So my last choice is an algorithm which is not particularly significant, but I like it for a number of reasons. So there's this problem which is probably used more often as a interviewing problem than it is in real life.
Ugh, that's my response to that. Ugh.
Yeah, it's one that I've actually done in interviews. It's the maximum subarray problem. So the idea is that you are presented with an array of integers meaning, both positive and negative whole numbers. And the objective is to find the subset with the highest sum.
Oh, you gave me this early on in hanging out. Like, this is like a requirement to be friends with you, I think.
Yeah, for many years when I was working at an unnamed internet company, we would use this as one of our interview problems. It has the benefit that most competent programmers will be able to come up with a brute force approach to it. Majority of people that we presented it to did succeed at it, but they would usually come up with either an order n cubed or an order n squared algorithm.
Mm-hmm. Compare every to every other. Yeah, that's
so you can sort of think of generating every conceivable sequence, every conceivable subsequence in the array, and finding the sum of those, and then just finding the
Yeah, I could imagine using a handful of nested for loops to sort of march some pointers through this array to find the maximum sum. That's the easy, greedy solution, right?
Yeah, and that's what most people do in a lot of applications. That's perfectly fine. Another interesting thing about this is it's discussed in the Programming Pearls book.
I remember that book. I had it. We had a rabbit that my wife found in the alley, and it chewed up it ate that book.
Yeah, they go back a ways, but
Well, I had mine had like a bunch of Fortran in it, but they were totally, I think it was Fortran. Maybe it was basic. It was readable.
he talks about this algorithm in the book as basically a way of like refining an algorithm. So he talks about the n cubed algorithm and the n squared algorithm, and then some colleague of his found an n log n solution, and then they presented this idea to a computer scientist at Carnegie Mellon named Jay Kadane, and according to legend, he came up with this algorithm, which is now called Kadane's algorithm, in less than a minute.
Jeez, I didn't know this had a name actually.
Yeah. So it's a very surprising thing that you can solve this problem by just making one pass through the array. It was obviously obvious to him, to Kadane, but not at all obvious to me. Even after describing it, it's not obvious to me. But
Wait. I'm pretty sure you told me about this, and I was like, geez, I don't know the answer to that. And I think I like went home, and the next morning I was like, oh, I think I have an idea for how to do it. And I came back and you were like, yeah, that's pretty close. I don't know if that counts as a pass. I mean, we ended up becoming friends, so obviously I passed.
yeah, I don't require my friends to pass programming tests.
Yes,
Just
sorry, that's a
to be
bad
clear.
joke. Yeah, it's not true. That's a bad joke.
I mean, it helps, but
Oh.
just kidding. I don't have any friends, so um,
Oh. So how do you do
so
it?
anyway,
Sorry, yeah.
so
What's Kadane's algorithm that he came up with in 1 minute?
so it's an example of what's called dynamic programming, and I don't want to go into that into too much detail, but the sort of crux of dynamic programming is that you can take a problem and break it down into sub problems and solve them individually. And so it's not exactly recursion, but it's got sort of the same flavor. So his insight was that you can keep sort of a running sum as you're going through the array, so that you only have to make one pass. So you start at the beginning, and the best possible sum is 0, and as you're going through, you keep a sum of everything that you've seen so far, and if as long as that sum is getting bigger, you assign it to the best possible sum. As soon as the sum that you're keeping track of goes down, there's this idea that Kadane realized that you could basically just start over.
You got a string of positive numbers and then a string of negative numbers. As soon as
Yeah,
you
so,
hit that first negative number, you like your string of positive numbers, you just add them all up. And then maybe I've got a like a swamp of negative numbers and then a whole bunch of positive numbers on the other side of that swamp, right?
so you're keeping track of this sum of everything so far, and you have what's called the best sum so far. So the best sum so far is the maximum of the previous best sum versus the current local sum, which is all of the numbers that you've seen so far. So what he realized was that, once the sum of all the numbers is lower than the best sum, you're just going to keep the current best sum the same. And he also realized that there's going to be a point where the local sum that you're keeping may actually be smaller than the next term in the series, in which case you can just start over. If you reach a point where the sum of all the numbers so far is actually less than the next number in the series, you can start over the local sum from that number again. I'm not sure I'm doing this well, but so this idea is you've got two sums that you're keeping track of. One is the best maximum that you've seen so far, and then the next one is this local maximum, which you can reset from time to time. And
Mm-hmm.
if the local sum that you're keeping track of as you scan through the numbers becomes larger than best overall sum, then you just obviously swap that sum with the best sum. So by the time you reach the end of the array, you have this best sum that you've found over the course of scanning through the series of numbers. So the reason why it's dynamic programming in this sense is because you're essentially reducing the problem to finding the sum in the remainder of the array, if that makes sense. So you're keeping track of the best sum that you found so far, and now you're just dealing with the rest of the array. So it's dynamic programming in the sense that you're kind of breaking the problem down into just dealing with the tail of that array.
I remember thinking if we go past 0 into the negatives, then obviously you could just start over again. But where it gets tricky for me is like if I've got a bunch of numbers and then they're all positive, and then I see -1, -10. Now I'm going back down, but then I see +5, +8, and maybe the next number is +20. It's like I need those negative numbers in the middle of my chunks of positive numbers. I need to do that instead of starting over again, right?
Right. So, just as sort of an example to maybe give a flavor of it, if you had an array that started out as 1, 2, 1, 4, let's say. So
those are all positive. So
yeah, that's right.
The
let's
best
say
subsum is like sum the whole thing.
Let's say 1, 2 minus 1, 4.
Right.
So you start off at the beginning. First best sum is 1. Then you hit that 2. Best sum is 3. Then you hit the -1, and now the sum that you're keeping track of is
local sum is 2 again.
The local sum goes back down to 2. So you know that you have a better sum. The better sum is the first 2 terms.
Right.
But you don't want to reset the local sum quite yet because it's conceivable that you could hit numbers that are going to make it go up again. So the current sum after you add the 4, it's going to go back to 6. So
6, that's your best.
Yeah. So now the best sum is going to be the max of the previous best sum and the current sum, which is going to be 6.
Mm-hmm.
But there are situations where the maximum of the current sum could simply become the next term. So,
right. Well, I think it's if you go all the way down to 0, if your local sum gets back to 0, you're like, okay, well, whatever I got to max before was good. I'm just going to start over with a new local at this 0. If I go all the way from there to there, I got a 0, then I don't even need to worry about what's in the past. I could just start from here, right?
Yeah, that's basically it. Is when the current sum plus the next term becomes less than the next term, you can abandon the current sum and just start over with X.
Okay, that's a better description than my grasping for 0. Okay, current sum plus the next term lower than the next term. That's pretty good actually. Yeah, that makes sense to me. Now, Mike, I sometimes wish I could get credit for just this hand wavy, fuzzy, like, yeah, but blah blah blah, and then it works. But no, we actually have to write this stuff down. So when you first asked me, do you have any favorite algorithms? I was like, I don't know. That sounds pretty dorky. And you were like, not Raft. And I was like, well, actually, yeah, that's a pretty good. I really like the leader election in Raft. That one makes a ton of sense to me. So that's one of my favorites. I would talk about that one. But I feel a little bit bashed about it because you predicted that that's something I would talk about. And so now I'm doing the predictable Eric thing and talking about a thing that you said, obviously, you're probably going to talk about. I'm being really predictable. I'm abashed about that.
Well, you're only being predictable to somebody who knows you well.
Okay.
So, somebody who does not know your history, it's like any prediction. You have to have some data to be able to make a prediction.
You got to be in a current state in order to predict about something that's coming next. You got to be able to look around.
Well, you have to know. If you're building a model of what's going to come next, you have to know what came before. And if people don't know what came before, then.
So you said to me not Raft, and I was like, well, that's not an algorithm, is it? But there is one part of it that I find pretty intuitive. So there's kind of a few pieces to the Raft paper. There is how do we achieve consensus. That's the Raft goal. You've got a number of servers. They call them servers in Raft. And they all want to agree on some stream of values. And the values is the whole state machine, right? So the idea is like you might send in a value like insert a record into your database Raft cluster. And then you might send in a request like delete that record from your database Raft cluster. And really what you're storing is this big log. First, the insert came in, then the delete came in. Obviously, if you have weird ordering with these instructions, then you get weird inconsistencies. So the goal is to have consensus. The goal is to have all of your servers agree what is the order of instructions that were received on our Raft cluster. And one of the ways Raft does this is it has a leader. And so every instruction actually has to go to the leader, and then the leader shares that instruction with all of the members of the Raft cluster. And so there's really like two ways to think about Raft. How does the log get added to? They call that appending entries to it. How do you build up that log? How do you confirm the structure of the log? And I didn't want to talk about that today. I actually find that to be the much harder part of Raft. The other part of Raft is let's say you want to have a leader. That's how Raft works. How do you make sure that the cluster has a leader over time? You may elect a leader, and then that leader the process might crash, or it might no longer be able to communicate. Maybe there's some crazy network problem. Maybe it just goes a lot slower. Maybe the network is fighting for resources with other things that are communicating over the network. So you might elect a leader, and then that leader just sucks. And so Raft has a proposal for how to fix this problem, and that's the algorithm for leader election. How am I doing so far? Is this making sense?
So far, yeah.
So you got one leader. All the instructions that go into the Raft log are going to go through the leader. And the problem that I want to try to describe is how Raft will conduct leader election. That's a whole process that the Raft nodes all go through. So the first important thing is that Raft starts with this configuration, and one of the configurations is called the election timeout, and this is a duration in time. And the paper gives an example of like 300 milliseconds. So that's the election timeout. And a Raft leader, whenever it sends out, oh, we got a new instruction, it sends out one of the RPCs that the Raft paper describes. There's a handful of RPCs, like message structure. There's a structure to these messages, right? And so this is the append entries RPC. And the paper says, you know what? The leader will actually send out append entries anytime there's new entries to tell the followers about, but it will also send out empty ones periodically to let the followers know, hey, I'm still here, I'm still alive. So there are actually three different types of server in a Raft cluster. There's a leader and a follower, and a follower and a leader can sometimes become, well, actually a follower can become, but not a leader. They can eventually go through a leader election if there's some problem with their leader, and the follower will turn themselves into candidates. So the way this algorithm works is if I'm a follower, I have an election timeout, and my election timeout might be 300 milliseconds. And what the Raft algorithm says is, well, we're going to pick a random value between half of my election timeout and my election timeout. So I'm going to pick a random value between 150 milliseconds and 300 milliseconds, for example. And when that time has passed, if I have not heard from the leader within that duration of time, then I'm going to call an election. So as long as the leader keeps sending out heartbeats to the followers will continue to just accept whatever the leader is sending them. When the leader seems to have dropped away, the followers are no longer receiving those heartbeats, or they haven't heard anything from the leader. In this random interval between, this example I'm giving here is 150 milliseconds, 300 milliseconds. They pick a number out of a hat. Then they will call an election. When the followers call an election, the first thing they do is they convert themselves into a candidate, and they send out these requests for votes. They send the request out to every single member of the cluster. And the algorithm says, if you're a member of the cluster, you get a request for votes, you immediately vote for whoever sent that to you, unless you've already voted. And there's another aspect to Raft, which goes back to back to Lamport clocks, for example, back to Liskov's view stamped replication. Raft has this idea of a term. The term is just a number that increments anytime you have a new election. So you start your cluster, nobody's a leader, there's no heartbeats, all the followers are waiting around. One of them randomly picks this number. Maybe they pick 160 milliseconds. Another follower picks 250 milliseconds. Another one picks 200. The one that picks 160, boom, wakes up and says, I'm a candidate. I haven't heard anything in 160 milliseconds. And it sends out a request for votes. All of the other followers are like, oh, sure, I'll vote for you. That first term, term one. Now, if that leader dies, the other followers, they haven't heard from it in a while. They pick a new random number between 150 and 300. One picks 195, another one picks 215. That one that picks 195 says, I'm a candidate. I haven't heard from a leader. My term before was 1. Now I'm starting a new election. The term is 2, and I'm going to send out a request to vote for votes from all of the members I know about in this cluster. And if the term is higher, that's one of the rules in Raft. If you receive an RPC and the term is higher than what you know about, you immediately go, oh, this is someone who's seen more than I have. So that follower that's on term 1 that's still waiting, its election timeout hasn't pinged it yet to wake up and call an election. It sees a new term 2 request for votes, and it's like, oh, we're on term 2? Okay, got it. I will vote for you. A candidate then will win an election if it gets a majority of votes from the servers in the cluster for that term. And it is possible for a candidate to call an election and another candidate to call an election, and then for majorities not to happen or other weirdness to happen. And so then they actually call a new election and they increment the term again. And the trick with Raft is that eventually it pretty much works out that you get a leader. That leader will keep going as long as it can communicate with the followers. The real dangerous thing in Raft is if you have a splitting of your cluster. So you really need half plus 1. You need a majority for a leader to be able to talk to. So that's the Raft leader election. I've never tried to describe it like that before. How do you think I did, Mike?
Pretty well. I think I probably could have benefited from a sort of whiteboard, kind of like X's and O's kind of demonstration there. But yeah, I get the idea.
It's really interesting because if you go back to FLP, the FLP result, Fisher Lynch Patterson, early 80s, right? The FLP result is a deterministic algorithm cannot achieve consensus in a fully asynchronous message passing distributed system if any single process can crash. Just one. It's like just one can crash. The whole thing can't achieve consensus. That's hard to believe, but that's what FLP says. There's a caveat. There's no upper bound on how long it can take any of the processes to reply, right? Any of the servers to reply. So there's no guarantee with Raft. It doesn't get around FLP. There's a mathematical block there. Like you cannot do this definitively. But with the randomness, with having an election timeout and picking a number randomly within that election timeout, you generally are not going to have followers becoming candidates at the exact same time. You'll generally have one follower become a candidate. And if you have enough to have a majority, you'll generally be making progress. Yeah, it's true. You've got to stop what you're doing for a leader election every so often. And it's true that having one leader does kind of limit you for scaling a little bit. All instructions really have to go through that leader. But it's a pretty cool algorithm, and it's actually not that hard, I think, to actually write this out, to code this up. The other parts of Raft are pretty difficult to code, I would say.
I will take your word for it.
So here we are again, and you look at something like FLP, and yeah, you can't get around FLP, but a little bit of randomness is the conclusion that you get from Raft. A little bit of randomness gets you kind of like circumventing a little bit. You're mostly going to win most of the time.
Yeah, it's a nice result. I can't remember how much we've talked about Raft in the past and how much of a more intuitive approach it is than the prior consensus algorithm, Paxos.
Paxos, yeah. I mean, they make that argument in the paper a lot that Raft is much easier to teach. They try to do a study on how easy it was to teach. The one example I would give there is a lot of Large organizations have implemented Raft. There's really popular implementations of Raft. Paxos doesn't seem as popularly implemented. So maybe the proof is in the pudding. You've got people building Raft, so probably it is easier to build and understand than Paxos. All right, Mike, I had a great time talking algorithms with you. We should really invite our listeners here, I think, to reach out to us. Let us know if we pulled this off or if we made it confusing. You can reach us again, podcast at picturemecoding.com. You can also reach us on Blue Sky under Picture Me Coding. Thanks so much, Mike. I learned some stuff this week. I had a good time chatting algorithms with you.
I'd also say that if you have your own favorite algorithms, please let us know, because there are millions of them. So
There's others. Yeah, I guess there's others. Yeah. All right, Mike. I'll see you again next week. Thanks so much.
see you next time.
Bye-bye.